Oh, would you mind? Thanks so much. I'm woefully unprepared. Ah. Are you going to do the honors here? Okay.
So it's our really great honor to have Doeleman, who's the director of the Relativistic Telescope, giving our presentation, our lecture today. And I don't think it's an exaggeration that this is one of the most exciting astronomical experiments in many decades. Really, we've been waiting now for a century. George Schultz you actually see a black hole, and over the decades, astronomical precision has increased so that we can see finer and finer and smaller things in the sky, and using not just one, but a whole array of ingenious techniques, they've narrowed down the resolution, and they've taken these photographs, which I think are very soon going to transform the whole world. We're going to have pictures. We're going to see black holes. It's just fantastically exciting. I've been excited about this as many others for a long time. Now, the pictures have been taken. The data is there. With an experiment that takes this long and so on, you don't just sort of stream the data out as it arrives. You have to organize it, keep it secret, and hasn't all been released, but today's the day, right, Shep?
You guys are in for a real treat.
So, I know they have the data. We're all on pins and needles. Probably not going to give it all to us today, but I think sometime in the next couple months, it's going to be, and I'm sure it's going to be all over the news and so on and so forth. And I think we should all be prepared to understand this really kind of amazing moment in the history of the black hole, when this weird mathematical reality has suddenly becoming a physical reality, and it's just really exciting. Shep has an insane schedule. He's flying around. All the observatories are in weird places on mountains and whatever, and between the meetings and raising money, and so I'm just really honored that he's taken a couple hours out to get us geared up to understand what it is that we're going to see in a few months when all the data is released. So thank you so much, Shep.
So thank you for that very generous introduction, Andy. Let me just say what I have to say, which is that we are still working on the data. The results are due out this year sometime. That's really all we can say at the moment. So we're kind of in this lockdown mode, and we are of course excited because we've been working on this for almost 2 decades, but we feel this could be our year, and so we're interested and excited to present that to you. And I want to preface this by saying that this is a very interesting year. In 1919, almost exactly 100 years ago, 2 expeditions set out by boat. From England, one went to Principe off the west coast of Africa, and one went to Sobral on the coast of Brazil. And the express purpose was to observe the 1919 eclipse, this amazing phenomenon of Earth and sun and moon getting together to provide us with a look at something that you wouldn't normally be able to see, the corona of the sun, for example, and some of the mountains around the edge and the limb of the moon. But the real purpose of that was to test Einstein's theory of general relativity, right? I mean, Einstein had predicted that there'd be light bending around the limb of the sun. You probably are familiar with this. The Newtonian concept of gravity, there was force-based action at a distance, predicted one value. And Einstein's deviation of starlight around the limb of the sun predicted twice that value. They looked at their photographic plates, and there was a little bit of concern about how those numbers were processed, but in the end, it was very clear that Einstein's prediction was correct and Newton's was wrong. And overnight, this new idea of gravity was born. And here we are 100 years later, kind of doing the same thing. There's nothing new under the sun, right? You think you have some amazingly new idea, and it turns out that all these pioneers and luminaries 100 years ago kind of thought of it first and had done it first. But we find ourselves now going, as Andy said, to all parts of the globe. And so we do think of ourselves as explorers, trying to look at light bending, as I'll show you, around a black hole. So going from the weak field of our sun to the strong field of the event horizon, the very limb of the black hole. And if we could do that, then we'd be able to test Einstein's theory in kind of imaginative and new ways, and I'll tell you about some of those today. But the real purpose of this talk is, as Andy said, is to make concrete something that has been very abstract for a long time. The black hole, it terrifies us. Getting an image of it would be iconic. And all interesting images are kind of terrifying. Recently, do you guys know what South by Southwest is? I really did not know what South by Southwest was, but I found myself talking at South by Southwest with the university professor Peter Gallison. And he showed some iconic images. One was the flea, the first image of a flea, which gave real vibrancy and reality to the microscopic world. One was the Earthrise over the moon. And we hope that if we can make an image of a black hole, it would join that pantheon of iconic images. So, without further ado, that's what we're here to talk about today. How do you turn an Earth into a planet-sized telescope and take, hopefully, a picture of a black hole? And I want to start off with this interesting image of a galaxy. It's a beautiful galaxy. This is the Centaurus A galaxy. And how many of you guys know about the EHT? Generally, a few people? OK, so maybe you've seen some of this before, but the other part here is that I'd like everybody to ask questions whenever they want to, because we're going to get into some of the details of how we do this. And I want to make it a little bit real. But the idea is that at the center of this galaxy, there is about a 10 million solar mass black hole. And we know there's a 10 million solar mass black hole there. At least we surmise there is because of this radio image, right? So you see in radio waves these intense outflowing plumes of relativistic charged particles that are streaming from the center. And they go, you can see they span the entire width and length of the galaxy. So there's something extremely energetic there. The only thing that we can think of that can produce that kind of luminosity, that kind of directed energy, would be a spinning black hole accreting fairly efficiently in falling matter. Okay, so we know there are these monsters inside these galaxies. And what would it look like if we could zoom in by, well, factors of 1 billion here? And the idea is that you can test the strong GR case by looking at the black hole silhouette, often called the shadow. And this is a schematic drawn by Jean-Pierre Luminet in 1979, who's going to be visiting Harvard, actually, at the Black Hole Initiative conference in the spring. I encourage everybody to come and check that out. And he saw that if you had an accretion disk, a pancake of material orbiting this black hole, that there was no behind of the black hole, right? So you see the back of the accretion flow flipped up. So if you want to hide behind a black hole, just forget about it. You're never going to be able to do that. But the important thing is here is this shadow feature here, delineated by this thin line here, is the last photon orbit. That's the photon orbit defined by light circling the black hole. And anything that goes interior to that would fall in. Anything outside goes on these parabolic or hyperbolic curves. And the important thing is that if you go to Einstein's equations, you can solve for the width of this shadow diameter. And it is the square root of 27 times the Schwarzschild radius. That's for a non-spinning black hole. So what I'm basically going to talk to you about today is the hardest way you can possibly imagine to calculate the square root of 27. Okay? You build a Earth-sized telescope, you image a black hole, you read it off. That's the square root of 27. Now, if the black hole is spinning maximally, then it's about 9/2 of the Schwarzschild radius. Not too different. And you'll see why that is in a moment. Because the closer you get to the black hole, the more the lensing of the gravity of the black hole increases. So despite the fact that when you spin, you get closer to the black hole, the photon orbit gets closer, it appears to be the same size. And this was looked at by Bardeen and Luminet and a host of other people. The basic point, though, is that the shadow size and shape encodes GR. If we could make an image of this, we'd be able to test GR. So we stand on the shoulders of giants. People were looking at the impact parameter of black holes as early as 1916. This is a photograph of a page from a book by Max von Laue. And you can see here that square root of 27 shows up very, very early in some of these calculations. That people asked, what would be the last light path away from the black hole that would reach us at infinity along a parallel line. Hilbert, I guess I got these out of order. Hilbert did the same thing around 1916. So immediately after Schwarzschild's solved the point mass solution to Einstein's field equations, we had these kinds of things popping up. Now, where are we today? Well, of course, now we have very fast, high-speed computers that can use flexible computing fabric either on the cloud or in clusters. And a number of our collaborating theorists have calculated what this would look like, including, of course, Professor Strominger, which we'll talk about in a little bit. But we've looked at what the emission in radio waves would look like around the black hole. And in all of these, you see a couple of characteristics. First, you see this circular feature here, which corresponds to that last photon orbit. That's the shadow size. The second thing you see is typically one edge of this is brighter than the other. And that's because of Doppler boosting. So even if you had a non-spinning black hole, the orbital motions of the gas around the black hole would Doppler boost emission, mostly due to synchrotron emission, in one direction and Doppler deboost it in another. So we're familiar with this from the relativistic electromagnetic equations, where you accelerate an electron and all the emission narrows into a cone in the direction of motion. Okay, and that's what happens here. The reason this is all synchrotron emission is because magnetic fields are swept up with the accretion flow, and they focus and they concentrate along with the heating of the gas. So you wind up with relativistic electrons, magnetic fields that are condensed near the horizon, and that gives you the perfect recipe for a soup of synchrotron emission. Okay. So that's what I wanted to talk about right there. Now, that's what light does, but matter does something very, very different, because matter can't go at the speed of light, of course. So here, you're constrained to move along matter orbits, and it depends on whether you have zero spin, whether you're orbiting against the spin of a black hole in the equatorial plane, or whether you're in a prograde orbit around the black hole. And the factor of the radius here from prograde to retrograde is a factor of 10. So unlike the light orbit, this is kind of a very important conceptual leap to make, the light orbit is unchanged as you go from high spin to low spin. But the matter orbit changes by an order of magnitude. This is how you measure spin, okay? Because if you look at the innermost stable circular orbit, the size of that orbit as a function of the spin of the black hole, it changes almost a full order of magnitude as you go from retrograde to prograde. And for two of the sources that I'll tell you about in a minute, you go from an orbital period of 54 minutes to 4 minutes. So if you could time these orbits, and we think we can time these orbits, then you'd be able to read off the spin of the black hole just by looking at a strip chart recorder of raw data. And I'll tell you about that also in a few minutes. And again, questions anytime. So the first stop is to ask ourselves, is there a source that we could do this for? I mean, yeah, it's all very theoretical. Sure, you can image a black hole, maybe. But where can we go in the universe? And there's two places that we think that we can resolve an event horizon. One is in the center of our own Milky Way galaxy. This is a VLA image, a very large array image at 2 centimeters wavelength. And what you're seeing here are streamers of hot gas funneling into the center of our galaxy, the Milky Way galaxy. This white spot here is a bright emission, a bright point source of emission that we think almost certainly marks a 4 million solar mass black hole based on its emission characteristics, which we'll also talk about in a minute, but mostly based on this movie. So how many people have seen this movie before? A number of people. It never gets old, though, does it? Right? And this star here that makes this full orbit has now come all the way down here and is past periastron again. Right? So they have exquisite orbital motions recorded for this object. And we know that beyond a shadow of a doubt, there's something there unseen in the infrared, unseen in the X-rays, that corresponds to about a 4 million solar mass. Now, the shadow diameter that I talked to you about before for a 4 million solar mass is 50 micro arc seconds. So if we're going to build a telescope that can see this, we need to build one that's equivalent to being able to see a grapefruit on the moon, or your favorite citrus fruit. Or it doesn't have to be citrus. It could be something else. Equivalently, it could be reading the newspaper in New York when you're sitting in Los Angeles, or my favorite is counting the dimples on a golf ball if you happen to be in Los Angeles and the golf ball is in New York. Those are all pretty equivalent. You can see I have some practice telling people what kind of resolution that we need for this. But don't let any of those fruit analogies take away from the fact that this is very, very difficult to do. And that has really taken a lot of the attention of many, many dedicated scientists over the past decade to figure out how to do.
How many years did that video cover? Yeah, I missed it.
So the whole orbit is, I think, 11 years for that to go around. So it's been, so it's been about, okay. So it's been about 20 years. No, I'm sorry, 16 years. It's been 1.5 orbits all the way around. And the precision has gotten better every year. So when they started this off, they were using speckle imaging. So the error bars were quite large. And as they went around the whole orbit, the error bars got tighter and tighter and tighter and tighter until at the very end, they're able to test, they're able to detect the Einstein redshift of the starlight as it passes near the black hole.
So how many?
No, he gets, you're the professor. He gets to answer the question.
Most of the information is from the yellow star. And how much of the information is being carried by other uncompleted orbits?
Yeah.
There's 4 times how much of it is from this particular star, and how much of it, if this star wasn't there, could be still.
If that star wasn't there, they could still make that measurement because they have some of these that you can see moving around, and they've made a full 3D model. So this only shows the 2-dimensional projection. They have a 3D model because they also have spectroscopy now with a very large telescope interferometer in Paranal in Chile. So they can get also 3-dimensional velocities. So with all of that, they have an extremely good estimate of the mass. And that's very important because knowing the mass when you make the image lets you make those tests of Einstein. If you don't know the distance, then you're limited by how well you know the distance to the object. Okay, because essentially when we look at images, we're making a measurement of m over d, the mass over the distance. We don't get a pure estimate of the size. Now that's different from the timing. The timing does tell you directly what the spin of the black hole is and potentially the mass because that doesn't depend on the distance. You're just looking at the time.
I take it that's one significant difference on the mass.
Actually, this is much better than that. I put this twiddle here, but this is now actually 4.1, and it's good to the second decimal point. So the estimate of the mass now is at the 1% level.
And how many Schwarzschild radius is that closest to point?
It's 1,400.
So they're close to being able to get the spin out of this, right?
Oh, no. They can barely get the redshift measurement here, but the orbits of these stars is almost entirely Newtonian. I mean, 1,400 Schwarzschild radii is really far away.
That's 1/10 of a percent Newtonian.
Around that, I think they put limits on the post-Newtonian parameters, but it's still in the very weak field regime. So there are other reasons why Sag star, which is that 4 million solar mass object in the center of our galaxy, is a good case for a supermassive black hole. I just showed you these. You have these orbits that come around. But also, people have used radio interferometric techniques to show that the source is not moving with respect to background quasars or background extragalactic sources. That means that while you see these stars moving around very quickly, Sag star is just sitting there. And if it was virialized, if it was moving as fast as the other sources there, there'd be roughly the same mass. And the fact that it's not moving that fast means it must be much, much more massive. So we know it has to be very, very, very massive, like 10 to the 5th solar masses. Also, we see short-time X-ray flares. So we see the source flare in the X-rays. Yeah?
What isn't it moving relative to?
It's not moving relative to background extragalactic sources. So sources that are very, very distant that are essentially stationary.
We would expect you to be moving somewhat, but that's...
Oh no, I'm sorry. So it moves as you would expect something in the center of the galaxy to move.
Right.
It has a proper motion,
Right.
but the deviation from that proper motion is essentially zero. Yeah, I neglected to take out the linear term there. Yeah. So Sagittarius star flares in the X-rays, so we know that there's some kind of activity happening on short timescales just from light crossing arguments. In the infrared, you also see background stars not changing much at all, but Sagittarius stars jumping up and down, indicating some activity on short timescales. And again, a light crossing argument just tells you that something has to be happening on scales of a few or 10 Schwarzschild radii. So now we're going to get into kind of how we image this. Okay, so we have this one source, Sagittarius A star, that kind of motivated everything. It was the first source that we thought, well, we can really do this for. So we want to do this in the radio, and the reason we want to do this in the radio is because of this Goldilocks problem. Maybe Goldilocks is a cultural reference not everybody gets anymore, but everything has to be perfect, right? So you need to be able to see through the Earth's atmosphere. Okay, that's the first thing. So radio waves can see through the Earth's atmosphere, X-rays cannot. Okay, if you want to do this from the Earth's surface. You have to be able to see through the interstellar medium. And as I'll show you in a moment, the interstellar medium blurs the radio images that we take. Is everything okay? You want some water? Or? Okay, just want to make sure you're okay. And then you have to see through the accreting material, which it becomes optically thick at low frequencies, right? Photons actually scatter off the relativistic electrons, so you can't see deep into the gravity well. And then you have to have access all the way to the event horizon, or all the way to the last photon orbit, right? Radio waves are the only part of the electromagnetic spectrum that can see all the way through there, and for which we have the angular resolution to make this image. That's why we use the radio. Okay, so, but a normal traditional telescope simply won't do. Okay, this is the Haystack radio telescope here. And if you used a wavelength, let's say, of 1.3 centimeter, and you took the canonical resolution equation, lambda over d here, where d is the size of that dish, you'd be able to see, 1.2 arc minutes, or the equivalent of a coin, half of a football away, like a quarter, 50 yards away, so forth. Now, in the St. Augustine Plains in New Mexico, you have this very large array here, where you can have up to 10, 15-kilometer baselines. And there, if you had this same wavelength, you could see, standing in New York, you'd be able to see a coin in Boston. That's, 1 milli-arc minute. And the real ticket, though, is to turn the Earth into a telescope. Imagine you took these radio telescopes and took them to different parts of the world and could connect them. Okay? Then you'd be able to see, from New York, you'd be able to see a coin in South Africa, or, that's 500 micro-arc seconds. And this is all at a wavelength of 1.3 centimeters. If you reduce this by another factor of 10, so you go to 1.3 millimeters, then you get in the range, 50 micro-arc seconds, where you can start to see that shadow. And that's what we're after with the Event Horizon Telescope.
Could you just say a few words of where this idea of turning the Earth into a telescope, how did it come up?
Well, first of all, people were doing connected element interferometry all throughout the 50s and 60s.
With little things like that.
With connected elements. So for example, these telescopes here are connected by a fiber, right? So you can directly correlate the two signals that you get, right? I mean, the way that one of these dishes works here, of course, is you have a parabolic shape. Light hits different parts of the telescope, and geometrically it combines at just the right time. So the plane wave that hits that impinges on that surface, all in synchronicity gets to the focus at the same time, and that's where you put your camera. So geometry is what does the adding for you, okay? When you have telescopes that are far apart like this, you still get those signals together, but you have to receive the signal, turn it into electronic signals, send it to a correlator that correlates it, basically multiplies and adds all those together, and when you combine the data, you get one Fourier spacing, as I'll talk about in a minute, and the transformation of those Fourier components gives you brightness on the sky. So you'll notice here that even the VLA does not fill the entire aperture. Okay, so this gets back to your question. The question was how you get a high resolution without building a single dish. And the first step was connected element interferometry, but then you had to compare each pairwise antenna to get a Fourier component. And then expanding this out to the Earth gives you that resolution, but now the real challenge is how you make an image when most of your lens is empty. That's really what has consumed us in the Event Horizon Telescope for a long, long time. And the idea here is that here you can use one frequency reference that stabilizes all of those telescopes together so they know that everything is perfectly synchronous. But how do you do it when you have telescopes that are tens of thousands of kilometers apart? Wait, let me, okay, I guess I'm gonna get to that in a moment. Actually, let me see if I'm just gonna, oh, I'm going the wrong way. That's why I'm having trouble here. Okay, I'm going to come back to that and say I want to answer this question though. So the whole idea here is that how do you make an Earth-sized telescope stable? Well, the first thing you do is you have an atomic clock at each of these sites. You need a hydrogen maser. It loses only 1 second every 10 million years. And that allows you to time tag all of the data that comes into that telescope perfectly. Then you have to process the data, which we do here in digital electronics, and we've spent the last decade kind of perfecting these digital systems so they can swallow huge bandwidths. Why do we need huge bandwidths? We need huge bandwidths because the higher frequency you go, the smoother your dish has to be. Okay? It's really hard to make big, smooth dishes. Right? You can't make a football field-sized dish that's so smooth that you could collect 1.3 millimeter radiation. Right? So what we do is we make up for that in large part by capturing huge bandwidths. So most of the telescopes that use this technique that I'm going to tell you about, this very long baseline interferometry where you spread the collecting area across the globe, record 2 gigabits per second. Okay, so 2 billion bits per second. In the EHT, we record 64 gigabits per second. So we had to completely revolutionize all of this equipment just to make these kinds of measurements. But the idea is that you have a very stable clock, you collect a huge amount of data, you essentially preserve the phase of the waveform in this electronics here. And you do this at different parts of the world. And these clocks are so stable that you can later play the data back, just as a de-recording, at a central correlation facility, compare them, and you wind up getting an interferometer that's as large as the distance between the telescopes. And that lambda over d is what determines the accuracy with which we can measure details on the sky. Okay.
How do you synchronize the clocks?
GPS. So GPS gets you to within about 10 nanoseconds. And then what we do is we correlate at a lot of different time lags. And we find the time lag that exactly corresponds to the perfect alignment of those signals.
It gets you within 10 nanoseconds, but then is that shift stable once you have it?
Oh, yeah. Yeah. So what we do is this correlator hides a multitude of sins. Yeah. So what's in here is a perfect model of the surface of the Earth as it's rotating. So we know where the telescopes are. We know how fast the Earth is rotating. And at any moment, we know what the offset in time should be for the time of arrival from Sagittarius A star to those two telescopes, and we take that out. We only look for the residual delay, if that makes sense.
Yeah. What about like fluctuations in the magma on the Earth? That doesn't affect it?
No. I mean, it might affect us, but it doesn't. The biggest problem we have, Andy, is atmospheric turbulence. That is the biggest problem. Because what does delay the light in radio wavelengths is water vapor in the atmosphere. Okay, and that's why we typically go to high sites, high dry sites. We go to the Atacama Desert in Chile. We go to the top of Mauna Kea in Hawaii. We go to the Large Millimeter Telescope in Sierra La Negra at 15,000 feet. We try to get above as much of the water vapor in the atmosphere as we can.
But you just told us the clocks are losing a nanosecond a week, right?
Did I say? I said 1 second.
10 million years.
10 million years. Is that a nanosecond a week?
Yeah.
It might be. Yeah.
So you're in trouble in 3 months.
Oh no. But we perform this correlation every 10 seconds. So all we really worry about is how fast is it drifting in 10 seconds.
I see.
Yeah.
I see.
Yeah. Yeah, these are exquisitely tuned clocks. I mean, so we've arranged it so that we have no coherence losses due to the stability of these clocks over a normal integration period.
And the vapor in the atmosphere, what is that? How much does that slow you down?
Okay, that's the problem. That limits us to about 10 seconds because the turbulence of the water vapor in the atmosphere can change the path length as things drift across the array. And there you're limited by the size of the turbules in the atmosphere and their water vapor content. And you can simply see that there are fluctuations as a function of time.
10 nanoseconds, not 10 seconds.
On 10, so we want to integrate at this correlator here for many seconds to get high signal-to-noise ratio signal. But during that time, the phase is fluctuating back and forth because of turbules in the atmosphere. So that's really what limits us. Although we have tricks around that, which I'll show you. I'll show you one of those tricks in a minute. So I want to go back to, okay. So let's think about Sagittarius star for a moment. This is just some astrophysics on Sagittarius A star. It's the Eddington luminosity for a 4 million solar mass black hole. That's the maximum amount of energy you could really get from emission from a black hole, is about 3 times 10 to the 44 ergs per second. The accretion estimates, like how much matter is falling onto it, is maybe 1.6 times 10 to the minus fifth solar masses per year. We calculate that just by looking at the gas motions around Sagittarius A star. If you had a 10% efficiency, then you'd expect a lot of energy from Sagittarius A star. But we only see about 10 to the 33, 10 to the 36 ergs per second. So Sagittarius A star is very underluminous. And we think that the reason for this is that it's eating very timidly. It's really not accreting very much matter from the gas around it. And it probably has one of these puffy accretion disks, an advection-dominated accretion flow, so that it is simply sampling from the surrounding region at a much lower rate than it could. Okay, so in that sense,
Is it possible that it's emitting in some other wavelength that we're not?
no, this is basically bolometric. It's mostly emitting in the radio. As I'll show you in a second, it's peaking in its emission in the radio. Okay. So the real opportunity here is that at 1.3 millimeters, as I said, over the diameter of the Earth, it's less than the shadow size, so we can do this. The Earth's atmosphere is turbulent, but the opacity is less than 1, so we can see through the Earth's atmosphere. This is the Goldilocks problem. And then, importantly, the interstellar medium scatters radio waves. And that's really important for this, because even if you had a perfectly crisp imaging apparatus, the image at the black hole would be blurred as it travels through the interstellar medium through free electron scattering. Okay? So what I'm showing you here is the size of Sag A star measured over many years as a function of wavelength, and here's the size. And this solid line here is the lambda squared scattering law. This is what you would expect from first principles, that a point source would be scattered as. And you see here in the 70s, people were looking at 8 centimeter wavelengths, and it follows this curve exactly. It's only when you get to about 1 millimeter here that for the first time you begin to see some intrinsic structure poking out from that scattering. Up until this point, most everything was described by a point source that was fuzzy from this interstellar scattering. So you need to get to these short wavelengths in order to see through that scattering. Also, the optical depth of the accretion flow starts to turn over here, so you start to see through the optically thick accretion flow that's falling onto the black hole. Most of the emission here, as you can see, is in the millimeter and submillimeter. So nature has been very kind to us. We could have been tripped up at any moment, but we have the perfect situation here to try to image a supermassive black hole. And then, as I pointed out here, we have smaller apertures, but we make that up in bandwidth and sensitivity. So we're able to get enough sensitivity to make these measurements. So this is just a slide that I tend to throw in that shows we need wavelength over telescope size. We want to see 50 microarc seconds. So we need something that's 10,000 kilometers across to get the angular resolution that we need. And I've already explained some of this stuff. By the way, this is also an unashamed advertisement for our group. If anyone wants to image black holes, please do. I want to point out that, and I will throughout the talk, that this equipment here was built by one of our postdocs, Laura Verticic, who has since gone on to bigger and better things. Now she designs, I don't know if she can even tell us what she designs, because she may be working in the defense area and making a lot more money than any of us. But she was really the brainchild behind some of these systems. So where are we? Well, about a decade ago, we made our first measurements of Sagittarius A star. And this is really what set us out on this path. So a little bit of history here. We had an array of 3 telescopes, one here in California, which is since no longer with us, one here in Arizona, and one in Hawaii. And the way to think about interferometry is you're asking yourself, how much energy am I receiving on this baseline from the source? Now, if you have 2 stations that are close together, lambda over d is pretty big. So I like to think of that as the beam, the range of space on the sky over which you're collecting radiation is big, or your resolution is very poor. So you expect to get a lot of energy. All the energy from the black hole emission region should be collected. But as you go to these long baselines to Hawaii, lambda over d gets smaller and smaller and smaller, so you're sensitive to a much smaller region on the sky. Now imagine the black hole has a finite size. When you have poor resolution, you're still seeing all the energy. When you have high resolution, you're excluding some of that disk, right? So you get less energy. And that's exactly what we saw. Okay, this is a fit to a Gaussian here. And the Gaussian had a full width half max of about 3.7 Schwarzschild radii. So we saw exactly what you would expect if we had resolved the emission around this black hole. So everybody should have a moment like this. I hope everybody in their career kind of is sitting at their computer screen saying, what the hell am I looking at? Right? Because that's what we actually said, I think, when we saw this. It was like, holy cow. Although I don't think we said cow. I think we said something else. But this basically told us that there was something that was very, very small there. Oops. And, let me just start that again.
How small?
So this was about 37 micro arc seconds across, which is equivalent for Sag A star of about 3.7 Schwarzschild radii.
But you're seeing much less total energy, right?
Yes. So well, this was just a model. So with only 3 stations, we can't make an image at all. All we could do is measure a size, assuming a Gaussian model. So if the image on the sky was kind of a Gaussian, like a centrally condensed region that falls off like this, what size would it be? That's what we asked. And when you fit this Gaussian curve, you wind up getting a full width half max here of about 4 Schwarzschild radii. Now, we don't think it was a Gaussian. We think it's much more complicated.
But what you would be seeing would be like the corona and everything, right?
Well, we don't know what we're seeing. All we know is that there's something very small.
But presumably bigger than 3 Schwarzschild radii or whatever the capture rate is.
Well, so here, let me can I answer that in one question, in one slide?
Yeah.
So this is how we understood this. So we thought we were going to see something that was 50 microarc seconds across, the size of the capture radius, the size of the photon orbit. We saw something a little bit smaller. And we went through the equations and we looked at the size of a photosphere as you got closer and closer and closer to the event horizon. And it turns out that once you get within the photon capture radius, you don't get any smaller. You get a constant value for anything less than that capture radius. That's this turnover right here. So this is the object diameter and how big it is apparently on the sky. So it falls down until you plateau out like this. We measured something down here. And the way we interpreted this gets to your point, Andy, was that we weren't looking at some smoothly varying thing around the photon orbit. What we were actually looking at was the Doppler boosted small region off to one side. So we interpreted this as really seeing for the first time something moving at relativistic speeds around the black hole, brightening a region that was smaller than the expected shadow size. And we figured that when we imaged this, we would then start to see the shadow coming all around the limb. Does that make sense? Okay. We had to think of something. I mean,
Sorry, I'm
you know, I mean, I have to say that part of writing one of these papers is like, what does this mean? You know. Yeah.
So you're looking at one region of the sky, right?
Yeah.
And that region of the sky, you're saying you don't think it was centered on the black hole. You think it was centered on the edge of the black hole.
Well, we surmise that. All we can say, the only thing we could say from this measurement was the size of the emission region we were looking at. Because we don't have absolute astrometry on the sky.
Right.
All we can say is we're looking at something within a region around Sagittarius A star, and it is this small. That's all we can say.
Yeah.
Right? So
So you could move the thing a little bit and see it come and go, right? You don't have to look right at the black hole.
so move it, and
You don't have to be looking at the black hole. You could look in the other direction, right?
what would that tell us? What?
Nothing, hopefully, if your experiment was working. If
Oh,
you
yeah.
pointed this thing in the wrong direction, hopefully you wouldn't see the same thing, right?
Oh yeah, I'm sorry. If you point at blank sky, you get nothing. Absolutely.
So you move it around, and then all of a sudden you're seeing something.
Oh, I see what you're saying. Okay, actually, the right way to think about this, you're really onto something. The right way to think about this is that when you do VLBI, you're cross-correlating these signals from one side of the Earth to the other side of the Earth.
Yeah.
Okay, and you're also doing something else. That's the delay.
Yeah.
But remember, now we're getting into the weeds here. I promised you that some of the details. Now you get some of the details. If who wants to be a black hole? Just raise your hand. You're a black hole. Okay. Students only raise their hand, right? So if this side of the Earth is moving away from you, and this side of the Earth is moving towards you, there is a Doppler shift. Okay? So not only are you looking for the delay between these two sites, you also have to Fourier transform so that you account for the frequency shift. So there's a delay and what we call the delay rate. Now, those essentially translate onto the sky because in an interferometer, if I change the delay here, I'm looking at a different part of the sky. If I add more delay, I'm looking at this part of the sky. So changing the delay in your interferometer setup actually is equivalent to changing your direction on the sky. Does that make sense?
Yeah.
Okay? And then by changing the delay rate, you also can change the direction on the sky where you have the maximum amount of change in velocity. So the rate and delay are equivalent to looking at a map on the sky. So we don't actually turn our antennas, Andy. What we do is in the correlator, we change rate and delay, and we can make a map of the sky, essentially. Does that make sense? Yeah. And what happens is that when you put the wrong delay in, you see nothing. When you put the wrong rate in, you see nothing, and that's equivalent to making a map of the sky. Does everybody kind of get that? It's actually quite cool, right? Because you're basically steering your antenna electronically. That's the magic of interferometry. Right. So we don't actually move the telescope over. We just, in the correlator, say, yeah, nothing there. Yeah, nothing there. Ah, that's where it is. And we tune up on it.
I see. And when you say you're seeing a Doppler, that's the two sides of the shadow?
No. That's the Earth rotation.
That's the Earth rotation.
Yeah, I'm just letting you guys know that there's a lot under the hood in interferometry, right? I mean, so you're doing GPS, you're changing the nanoseconds of delay, but then you're also taking into account the fact that the photons here are at a different frequency, and you've got to adjust them to get that correlation. So I'm going to go on because I know Andy has more questions, so I'm just going to keep going here. Anyway, so we understand this. Here's the other Doppler shift, Andy. So the way we interpreted this is that here's the shadow size, which is 50 microarc seconds.
Yeah.
But we thought, oh, what we're doing is we're getting a little cross section here from this Doppler boosted bright spot.
That
Okay.
Doppler boost is from the black holes.
Yeah, indeed, but it changes the size of the emission. And so we measured a small emission size that was smaller than this diameter. And we said, oh, we think what we're seeing is the natural consequence of Doppler boosting from the black hole.
So you already think this thing is spinning?
No, even if you had a,
If this weren't spinning, you wouldn't see that.
yes, you would, because the,
It would be on both sides.
no, because in the, even if you had a spin 0,
Yeah.
and you're in the equatorial plane, this is still Doppler boosted at about a third the speed of light. And this is still Doppler deboosted at a third the speed of light away from you. You still wind up with an asymmetry. So matter orbiting the black hole is simply going faster this way than it is this way.
Because you're assuming this stuff is coming off the accretion disk, not back.
Exactly. Exactly. Okay. Okay, so how are we doing for oh my God.
You have till
I know, but
now till 6.
okay. I just this is a lot of fun. So and tempus fugit, right? Thankfully we have another source to look at. So we had the foresight to find another, to look around and find another source, M87, Messier 87, also known as Virgo A. This black hole is estimated to be more like 6 to 7 billion solar masses. That's billion with a B, okay? And at longer wavelengths, you see this tremendous movie made by Craig Walker and his collaborators. They were one of the first to make these tremendous movies of quasars. And you see this relativistic jet streaming out, very akin to that image of Sene that I showed you before with those directed jets. Now this is only one-sided, and that's because we think that this jet is coming almost directly at us, okay? And that the counter jet exists, but it's Doppler deboosted away from us, okay? And the center here also marks probably a supermassive black hole. And we think generally what's happening here is you have an accretion disk orbiting around. You have magnetic field lines either entwined in the disk or rooted in the black hole itself. Like an egg beater, these charged particles are constrained to move along these black holes. That gives you the synchrotron emission, and they're whipped around and accelerated to relativistic speeds by these magnetic fields, like a bead on a wire. Magnetic monopole. Andy? When magnetic fields go into a black hole, that's not a monopole. It's a dipole. Yeah, it winds up being essentially a dipole. Yeah. So this is basically the idea here. So there are two effects. One is that the magnetic field lines go into the black hole. Another is that they're rooted into the accretion flow. Right? The dense accretion flow ties them down, and they shear, and they start to accelerate particles from the north and south. And then one of our colleagues, Kazuhiro Hada, had this other tremendous result in which he saw at different frequencies the core of this source walk inwards towards a fixed point. And that's exactly what you would expect if you had this supersonic nozzle of this jet coming out of the accretion flow. You would expect that at different frequencies, it would become optically thick closer and closer and closer to the black hole. And that's exactly what was seen. So we think we understand, as 8 years ago, that we were looking at this supersonic jet or relativistic jet that was walking back to the position of a supermassive black hole here.
What's the opening angle of this jet?
It's a very good question. It's very difficult to estimate. We have some limits on it because we only see one side of the jet and not the other. We also see the extent of the jet. We think that the opening angle is probably very far out. It's on the order of tens of degrees, maybe 10 degrees. Close in, it kind of becomes a parabola, and you get a very wide opening angle, probably close to maybe 40 degrees.
That's the distance in the order of the Schwarzschild.
Probably like 10 Schwarzschild radii, something like that. So we think that at the range of the Event Horizon Telescope, we're looking at a very broad opening angle. Yeah. One of the interesting questions is it coming right at us? Is it slightly offset? We think it's probably at about 20 degrees offset, approximately.
What are those lines on a picture?
There are a lot of lines. Which one?
The black curvy one?
Okay. Oh, these are contours of radio emission. So you see, like, most of the emission is focused here, and this is in the jet that's going out.
Contours of constant intensity.
Of constant, yeah, Stokes' eye.
So it's strongest right in the middle, and then it's...
Yeah, so if you look at the, so basically it's a contour map of this image, right? So you see most of the emission here right close to the black hole.
It's constant frequency. Is that frequency, the color there?
No, what you're seeing here is intensity of total emission. all this is really saying is that most of the emission is focused here near the black hole.
How big is the black hole on that picture?
Oops. About the size of my laser pointer. Really? Well, you look at it this way. The shadow size for M87 is approximately that for Sagittarius A star. And this is 1,000 micro arc seconds. So it's a 20th of one of these ticks is the size of the black hole, Andy. So
It's a little bit smaller than one of those pixels. These little pixels on your picture.
yeah, maybe. So I mean, a 20th would be maybe this much. I don't know. I can't do the. So it's maybe twice the size of my laser pointer.
So why should we be able to see anything with all that junk in front of it? Is that a different frequency?
Well, exactly. So this is basically 7 millimeters. We're going all the way to 1 millimeter. This all becomes transparent at 1 millimeter. So we did the same kind of thing in 2012. We made the same kind of measurement. I'm not going to belabor this. But we found a size of 5.5 Schwarzschild radii in this source. And again, we thought to ourselves, well, how do we interpret this? Because here's a case. What's your name? Shahar. So what Shahar said, like, what's the opening angle? What's the directionality of this? Because this is coming right at us, we probably are looking at something orbiting in the plane that we're looking at. Okay? So you don't necessarily get this Doppler boosting and deboosting with a small emission size here and nothing over here. So we thought to ourselves, what we might be seeing here is the ISCO, the innermost stable circular orbit. And if we were measuring the innermost stable circular orbit, that changes with the spin. Because remember, I told you that that's the one thing, the innermost stable circular orbit for matter, that does change dramatically with spin. And we went through.
If it's at 20 degrees, 15, 20, the light from the innermost stable circular orbit wouldn't be able to get to us.
It wouldn't be able to get to us. Well, I can show some simulations. We've done some GRMSG simulations at that inclination, and you do see emission all around the edge.
At that spin?
Yeah. I mean, I'm sorry, that's the apparent ISCO, right? The ISCO, the light from the ISCO doesn't come directly at us. Light from the ISCO goes out this way,
Yeah.
and then parallelizes all the way out. So you get a much, much larger apparent size. Does that make sense? It doesn't make sense. So
I thought it can't. I thought it can't cross the 37-degree line. Well, it's within 10. Yeah.
say it again.
Okay, we can talk about it.
Oh, okay, yeah. Well, what I can say is we simulated this, and I'll show you some simulations here, and it seems very clear that you can get emission from that side.
If you go back a slide, this graph that you get here, as
Yeah.
well as the one that you had for the earlier
Mhm.
array of just 3 telescopes, why are all the data in these 2 clusters? Why can't we get anything in the middle?
Oh, thank you for asking that question. The reason for this, we're going to be here till like 8 o'clock. Wait, where am I? Okay, so the reason is the geometry of the array. We have a short baseline, and the baseline length here, which is kind of equivalent to resolution, is so all this cluster of points here is everything from these 2 telescopes.
So if I had a very good distribution of point-wise, pairwise distances, I'd be able to get a lot more varied points along that curve.
And what is your name?
Right.
Right, that's exactly what we've been doing for the past decade, Brian. Really, I mean, you've hit the nail on the head. We've spent a decade filling all of this in to make an image. Okay. Okay. So very quickly, if you associate the size we measure with the ISCO, you can write equations down and do simulations, and you can say, if my black hole spin goes from 0 to 1, prograde, retrograde, what is the apparent ISCO diameter? Because as Andy and I were discussing, if you have the ISCO, things are rotating like this, light doesn't come directly at you. You don't see the size of the ISCO. light comes out this way and is bent by the black hole, so you wind up with a magnification factor. So if you have 0 spin here, the ISCO actually appears to be about 7.35 times the Schwarzschild radius. Okay? And if you're on retrograde orbits, it can go all the way out here to just above 10. And if you have prograde orbits, it can go all the way down here to much smaller, to like 4 or so. And we did some simulations, and we looked at a range of different models. And this is our size that we measured here, again, about 5.5 Schwarzschild radii. And it intersects all the models that we looked at a spin of about 0.6. So we think that this is one estimate, only one estimate, Andy. I know you want this to be a near-Kerr black hole. I know you want it to be a near-Kerr black hole. But the estimate, it is a Kerr black hole. Of course it is. Why wouldn't it be? I misspoke, clearly. Right. Extreme Kerr, yeah, extreme Kerr. But our humble measurement, which could be wrong, was, and it's very model dependent, was that it was about 0.6 times the maximal spin. We know them. Well, that's a very good question. And what is your name? Mohammed. Very good question, Mohammed. We know it because we look at stellar dispersion. We look at the motion in aggregate of stars around the center of the Virgo A galaxy, and we model it. This is not work that our group does, but optical astronomers do, and they get one mass. That's about 7 or 6.5 billion solar masses. An equally hard-working group looks at gas dynamics around the center. They come up with about 3.5 billion solar masses. So we only know to within about a factor of 2. This assumes the larger mass. Okay? If we were to succeed with an image of this black hole, we might be able to resolve that mass discrepancy. Okay. You have very good students, Andy. So the last thing I wanted to say about precursor measurements is this. Andy asked, are we looking at total intensity? And the answer is yes, we're looking at total intensity. But we also receive all Stokes parameters. We receive 2 polarizations at each of our sites. We typically do use circular polarization, so right circular polarized light and left circular polarized light. And then we can form all 4 Stokes parameters, right? Left versus left versus right versus left. We get everything, and that means we can make polarization maps. And what Michael Johnson did when he first got to SAO, he was a postdoc, and now he's a federal scientist at the Smithsonian Astrophysical Observatory here. He converted those baselines. So what you're seeing here is east-west baseline and north-south baseline. So each of these points represents a baseline pair. Okay, so either Hawaii to California or California to Arizona. And what he noticed is that you could look at the amount of polarization here. So on very, very low resolution baselines, California to Arizona, you saw almost no polarization. Okay, and that's normal, right? You would think that a priori. Why? Because imagine you had very complex magnetic fields twisting around the black hole. If you had a big area that you were averaging over, you'd get what you call beam depolarization, and you'd find very little polarization. But as we went very, very far out, and we looked at much finer measurements, we saw increasing amounts of polarization. And this is indicative of synchrotron emission, because synchrotron emission, when you have electrons moving around magnetic fields, they have a preferred orientation that matches the magnetic field, and you wind up getting linear polarization in your results. So we expected, when we looked at very fine-grained images or very fine-grained interferometer readings, that we would see more polarization. And in fact, we did. And this gave us confidence that we could not only map total intensity, but we could map the magnetic fields around the black hole itself. Yeah?
Why is it that you care about east-west baseline and north-south baseline? Like, why are the 2 directions?
It's only one parameterization. We have to organize our data, and so we do it in these 2 fiducial directions, east-west versus north-south, because we can look at the Earth and measure that off pretty easily. We could use a different basis set, but this is what we happen to use in interferometry. There's nothing mystical about that. The last thing I'm going to say before we get to some of the other, what we want to do next is that phase is really important. Yeah?
Sorry, in the previous plot, what is that error with the time going forwards?
Which one?
On the
Time.
left side of this plot.
Oh, okay. So that's a very good. What's your name?
Arthur.
Arthur. Okay. So you guys are very sharp. So as the Earth turns, these two telescopes move in a predictable direction, right? So the east-west and north-south components of the baseline change with time. And this just shows you that Hawaii to California changes in this direction. So when you have that particular baseline looking at that particular point in the sky at that particular time, that's what the baseline actually does. I still find this to be amusing and amazing at the same time. The fact that your telescope is actually moving and changing as the Earth rotates. Right? We call this Earth rotation aperture synthesis. We fill in the virtual mirror by letting the Earth rotate under our feet.
So the way you're measuring these baselines is considering like just this projection watching the Earth spin. So like you like it would seem that since like it's if I was just saying like, oh, it's my baseline on the Earth, like that's not changing. But you're saying like from a sort of like an external view on the Earth, it's moving relative to this point.
Exactly. So think about these. Think about these baseline directions from the black hole. Imagine you're sitting on the black hole. You're looking at the Earth. You would see the baseline between these two change in its projection towards you. Does that define things?
Yeah.
Right. So it's not north-south like, from like Magellan or something like sailing the Earth. It's north-south when you look at the Earth from a particular direction. Okay. Another postdoc of mine, Rusen Liu, who's now at the Shanghai Observatory, he made some of the first observations using these interferometers that retrieved not only total intensity but phase. Okay? And this was important because this was the first time closure phase was measured. Now, what is closure phase? Well, normally, if you have two baseline, if you have two antennas, imagine a cloud of water vapor goes above one of your antennas. Well, you're challenged. Again, different word. You're challenged because the Fourier component is, of course, complex. It has an amplitude and a phase. Normally, the phase would only be due to the source structure on the sky. But if a cloud moves in front of one of your antennas, it changes the phase completely because the path length changes. Okay? So the phase is meaningless on a single baseline. The trick is to use a triangle of 3 baselines. Okay? Because if you have a cloud above one of your antennas, it will affect the Fourier phase of this baseline with a positive sign, and the phase on this baseline with a negative sign, it cancels. So by adding the interferometric phase around a closed loop of stations, you are immune to all the atmosphere above the stations. This was a trick that was invented in the 50s by Jennison, a radio astronomer from Britain, and then was brought back to life, as they say, in the 1970s by Alan Rogers at the MIT Haystack Observatory. And it is the fundamental basis on which we do all of the VLBI imaging that we do. The fact that you can recover phase, even though these sites are very far apart and they're not tied together. So,
Why is it positive for one and negative for the other? Does it have to be a certain
well, it's just the ordering. Yeah, well, it depends on the ordering, but as you go around the closed loop, then no matter how you do it, it always comes in with opposite signs on those 2 baselines. So Rusen made this lovely map of this quasar 1924 minus 292, and he showed this closure phase here around the loop of the 3 baselines, and he was able to discern different models, and we all rejoiced because this was a real leap forward. Now, why does phase matter? Who's seen this figure? Is this figure shown anymore in any class anywhere? Okay, so this is a picture from Oppenheim and Lim. What you see here are 2 images. Does anyone know who this is? No. Does anyone else know who that is? Oh my God. Oh my God. Okay. Must keep going. Must keep going. Okay, this is Walter Cronkite, who for many years was kind of like the voice of all knowledge and news in the United States. This is a clock. I'm not even gonna let them. I'm not even gonna. Yeah, I'm like, yeah, like, yeah. Have you guys ever seen these analog? It's right over there. Oh my God. Okay, we keep going. We soldier on. So these are two images. In this one, so what we've done here is they've taken the Fourier transform of these two images, and you wind up, of course, with phase and amplitude. In this case here, we've taken the phase of the clock, merged it with the amplitudes of Walter Cronkite, and done the inverse Fourier transform. Okay, so let me say that again. The phases of the clock merged with the amplitudes, just like grafted them on. Crazy. That's like a Frankenstein thing. And you perform the inverse Fourier transform, look what you get. Most of the information about the actual image is stored in the phases, not in the amplitudes. Same thing for Walter Cronkite here. You take the phases of Walter Cronkite, add the amplitudes from this image, just graph them on. Crazy.
Sorry, Shep, what are the phases? I thought that it's a black and white piece of paper. It has only...
No, but you take the Fourier transform of it.
The Fourier transform of the phases in the Fourier transform.
Exactly, right? So you take the Fourier transform of this image, you get amplitude and phase at each pixel, the Fourier transform of this one, and you just mix up the amplitudes and the phases. And most of the information about Walter or the clock is stored in the phases. I'm just giving you an illustration of the fact that phases are really important. Being able to measure the phases on an interferometer lets you make these images. So where are we now? This gets back to, remind me your name again? Brian, sorry. Okay, so everything I've shown you so far with these 3 sites here, you can do a lot with 3 sites. But you can't do everything with 3 sites. So now we've branched out to the Large Millimeter Telescope in Mexico. I had curry with the director of the Large Millimeter Telescope in 2012 in Garching, Germany. And we said, let's do VLBI from the LMT. And a year later, we had interferometric fringes from the LMT. So when you want to, you can move very quickly. And the other thing I would tell you is, if you do want to do something in science, don't listen to anybody who tells you it can't be done. Just do it. That's my one bit of advice. Don't wait for permission. Ask for forgiveness. And next, we phased up all these dishes here at ALMA. We started this in 2011, and we developed an entire system to turn this connected element array into one virtual single dish. So instead of having many recorders at all the different 60 dishes there, we have one recorder after we digitally sum all the signals from those dishes. We have our colleagues in Europe have added the 30-meter telescope on Pico Velita in the Sierra Nevada. And this is Plateau de Bure, the interferometer in the Alps in France. And then we now have, of course, fringes to the South Pole. There's a 10-meter dish there. And we've adapted that for use in VLBI. So basically what we've done is we've taken a heterogeneous array of telescopes that were not meant to do this work. And we created instrumentation that we could take at modest cost to each of these sites, bolted it in place, and turn them into elements of an Earth-sized array that could image a black hole. That's my elevator pitch.
And there's nothing in Asia and Africa because there's no telescopes there?
Well, okay, so first of all, we've added Greenland. And second of all, there are a couple of places here in Africa that we're looking at to build a new site, but they don't exist yet. It turns out that Africa, there just really isn't a lot of millimeter sites because there's not high and dry spots. It turns out that even Mount Kenya here and Kilimanjaro, they're very high, but they're in this equatorial soupy range where you wind up with this rainy season and you still get some water vapor that comes up. The Ethiopian highlands here are at an altitude of 4,500 meters, but the rainy season just kills you there. So even though it's high, it's not as dry as you might think. So we are really tied to the Earth.
In Asia also?
In Asia, they have some high sites in the Himalayas, for example, but the problem there is that there's no mutual visibility with most of the other array. So we'd have to make a very big investment in Asia to extend the EHT there. We could do that, but adding a single dish there doesn't help us. Yeah. So I'll give you an example.
Australia, though, you could.
Yeah, but Australia, it's like, what is it, Ayers Rock? I mean, you know, it's just not that tall. You know, did I say the wrong thing? I shouldn't have said that. I love Australia.
I don't think they let you put a telescope on top of it.
Honestly, I mean, and it's really true, and nor would we want to. Okay, whoa, I got to walk that back. First of all, deeply respect Ayers Rock, and second of all, I was just using it as an indicator that there are not a lot of high places in Australia. That's all I meant to say by that. Andy, I'm never speaking in your class again. All right, where were we?
Wait, but couldn't Himalayas see things at the same time as Hawaii? They're not.
No, okay, so it turns out that ALMA is one of the key sites here. It is by far the biggest and largest aperture we have. It grounds the sensitivity of the entire EHT. And we need it for some reasons that I'll talk about at this rate tomorrow. But the problem is, so for example, you can't even see Japan. There's no mutual visibility for Sagittarius A star or M87 between Chile and Japan. So by the time you get to by the time you get to Asia, there's just no mutual visibility with our key site here. Now we could get other
It's all
sites.
anchored on ALMA.
It is anchored in ALMA at the moment. Yeah.
Would it be beneficial to have smaller aperture telescopes, but many of them everywhere?
What is your name? Achilles. Okay. Oh, I recognize you from the papers that you write with Andy. That's exactly what we have to do. I'll just leave it at that. That's exactly what we want to do, and I'll show you something about that a little bit later. Okay, so here's how it works. You might think, well, how does this actually work in practice? So here you see these red dots are in real time. We acquire M87 with Greenland and Europe, and then we get all of these different combinations. You can see that over the course of an evening, all of these busy bees of these baselines sweep out more and more of the Fourier plane. So each point here is one Fourier component, and you get enough over a course of an evening that you can make an image. So now I'm going to get into some of the details, just to let you know that we don't just sit around on the couch eating bonbons. We actually go to these sites. We actually work. We actually create new systems in electronics that allow us to adapt this heterogeneous array to the VLBI case. So one of our biggest challenges that we took up starting in 2009, so it took us 10 years to actually bring this to fruition, was to combine all the light collected by these 60 dishes in ALMA into one digital stream. It's really hard to do because you're operating with many, many data streams, high data throughput, and you have to make sure that for a 1 millimeter wavelength that you're doing this all within a tiny, tiny fraction of a wavelength. Okay, so you have to do this within microns of path length. And it turns out that we were able to do this. We roped in a big fruit salad of funding agencies and institutes. And what you can see here is you can see the root mean squared variation of the phases across the entire array. And this is a full 2 pi, meaning it's totally ambiguous. And when you turn on the phasing system that we built, it immediately cinches up, so you wind up with a mean RMS of about 9 degrees here. So meaning that we're suffering no coherence losses, we can really turn 50 dishes into one dish. Okay, and that took us a long time to be able to do. And this was our first detection from Spain to Chile at 1.3 millimeter wavelengths. For a while, this was the world record of angular resolution from the surface of the Earth. Applause later, clearly. Yeah.
Do you still have the record?
Yes.
Is it just-
Yes. Well, yeah, because we're the only ones making the record. Like we just, it's like so. What I will say, from the surface of the Earth, I mean, there are ways to get better angular resolution if you're off the Earth. But the best, the record right now is held by us. And that's because we went not to 1.3 millimeters, but to 0.87 millimeters. We did the first 0.87 millimeter VLBI ever, and that was from Chile to Hawaii. And that was a fringe spacing of 19 micro arc seconds. And that is the world record right now. This is some of the, this is kind of a rogues gallery of what we had to do over the past decade. This is Gisela Ortiz, who was a graduate student at UNAM in Morelia in Mexico. And she's here working on the atomic clock, which we transported to the large millimeter telescope, which is shown here. She was with us for some of the first observations that we made there. She's now at Max Planck Institute for Radio Astronomy. This is the Apex telescope near ALMA, but separate from that. And so we got our first fringes to that site in, let's see, when was that? 2015. This is the South Pole telescope, and this is the first interferometric fringe we ever got to the South Pole telescope, also to the Apex telescope. And then this is the IRAM 30-meter telescope in Sierra Nevada. This is a great place because you can go up there by snowcat and then ski down, so it's really nice. One of the only observatories I know of where you can serve wine at dinner. Most of them are dry. And here you see, what? That's no, you can't drink. Usually you don't drink at these altitudes because it really does a number on you. And this is IRAM this is Spain to Chile. Now, what can we do? So, by the way, everything I'm showing you are simulations. There's no real images or data here at all. I just want to point that out to you because sometimes people make a mistake and they tweet something and I get in trouble. So in 2013, of course, we only had a few stations, so we swept out just a few arcs in the UV plane, or in the baseline plane here. In 2017, if we only had OPEX, we would have swept out everything in blue here, but because we had ALMA, we were able to recover everything here. So these sites here, we would have, so these tracks here mark baselines where we could observe, but we didn't have the sensitivity to detect Sagittarius A star or M87. But when you added ALMA, you can see everything. So all these little gray points here become blue points because we can detect the source. That's why ALMA is so important for what we do. We can detect everything on the baselines we need to make an image. And if we have a simulated image here from general relativistic magnetohydrodynamic simulations, and we create fake data sets as though we had observed them with this array, and we try to image them without ALMA, all we get is kind of a blob here. But with ALMA, we can hope to image the full circle here and measure the shadow diameter. Now, we've done some pretty interesting things because we asked ourselves, how well can we image? Because really, you don't want to...
That simulation is using a preferred A of 0.6?
No, I'm sorry. This is Sag A star. So this is a simulation of Sagittarius A star. And we think Sagittarius A star is not spinning much at all.
I see.
Yes. Say it again?
That shadow is a perfect circle.
Yes. So I'm going to just tell you a couple of the details here. We asked ourselves, if we had fake data sets, how well could we recover the shadow? Okay, so it's a little bit like, are you guys familiar with LIGO, the Laser Interferometer Gravitational Wave Observatory? So they basically tested all of these different possible ring downs, all these possible mergers to look for gravitational signals. We essentially did the same thing here. We looked at all these different simulations. We made fake data sets as though we had observed them with the EHT, and we said, how well can we recover the real truth image? And we did this over and over and over and over again to refine our imaging methods. And this was really led Katie Bauman at MIT, who's now a postdoc here with us at SAO, soon to become Caltech faculty member, led that with Kazu Akiyama at MIT, Andrew Shale at Harvard, and again, Michael Johnson, who's at SAO. They really pioneered a lot of this with colleagues around the world. So here's one of the slides I like to show. Maybe some of you have seen this, but this is the truth image here. And all of these, actually, is that the truth image? No, I'm sorry. Okay. All 6 of these are image reconstructions based on fake data. Yeah.
So what is assumed in this simulation about what is generating the light?
It's all synchrotron emission. It's all hot electrons moving around in the presence of magnetic fields. And it's a kind of a self-consistent GR-MHD simulation. So they put a bunch of particles in, they put a bunch of magnetic fields and let it evolve. And you wind up seeing just circularization and then jets forming, things like that. So
Do we understand why that should peak at the submillimeter?
well, it's typically because of the range of energies of the electrons and the magnitude of the magnetic field that you would expect from an accretion flow that's been sweeping things in from a given distance. You wind up just getting, for these particular sources, a peak around the submillimeter. It's not uncommon. There's something called the submillimeter bump, which is typically seen in some of these quasar sources. And they presume that is from the synchrotron emission. So just to let you know what's happening here, we took a truth image, we created fake data, and we gave it to 6 different groups, and we said image it. And they all wind up seeing kind of the same thing, giving us confidence that we can recover the truth image, which is what's shown here. Okay? Now, it doesn't always work out so well. These are some very early attempts, and you can see there's some similarity here. These 3, for example, are showing some kind of shadow feature, but arguably these aren't, and this one shows some kind of like deep sea dweller. And the answer here is that, well, it's a complicated emission structure. The jet here is coming at us, and it has these shocks or these filaments, and it confuses the imaging algorithm. So this sends you back to the drawing board, and you ask yourself, can I make an image reconstruction algorithm that's more robust? We also occasionally send things through the pipeline that are just different. I think some of you guys have seen this before. The answer is it's a snowman. But it's important to do these kinds of, we're not just playing around here. You need to throw into the algorithm really weird things so you can be sure that if there is something odd there, you will see it. Okay? So we spent over 2 years working on these kinds of algorithms to make sure that we knew what we were doing. And I'd like to show this. I mean, yeah. So actually, my wife works with AI a little bit. And she gave this to me, but you want to be careful not to try to see shadows, because if you think you're trying to see something, you might not see the right thing. It turns out that labradoodles and fried chicken are almost indistinguishable when you see them from afar. And then, of course, there's chihuahuas or blueberry muffins. So you want to be very sure you know kind of what you're looking at, because you could easily be fooled, right? So this is why we've spent so much time and attention to this very important scientific work. This is what Andy, I think, will care about deeply. I told you before we're looking at magnetic field structures because we have access to all 4 Stokes parameters, Q, U, I, V. And here's a model where we show in ticks the linear polarization of the synchrotron emission coming from near the black hole. And with the array we were fielding in 2017, we really couldn't recreate this kind of structure. But in the array we fielded in 2017, we feel we have a pretty good shot at recreating the magnetic field structure that's evident there. And Andy and his team have come up with a very interesting way and predictions of looking at the magnetic field around M87. And so we have a shot now at taking conformal field theoretic approaches to the magnetic field around a near Kerr or extreme Kerr black hole and testing it with the Event Horizon Telescope.
Is this from the edge on, or from is this supposed to be Sagittarius star?
No, this is actually M87. I believe this is M87, and this is showing kind of near face on. Oh, okay, we could talk forever. Before I told you about closure phase, so I'm not going to go over that again, but there's this magical observable where you sum interferometric phase around a closed loop, and you don't image, you just look at the time variability of that closure phase, and you can see things evolve in real time around Sagittarius A star. Why is that important? GM over C cubed, the light crossing time of the event horizon for Sagittarius A star is 20 seconds. The innermost stable circular orbit period is half an hour. So while the Earth rotates in half an hour, you see many orbits. So if there's something weird orbiting the galactic center, I'm not going to say an alien civilization or anything like that. But if there is a magnetic reconnection event that injects heating and affects the charge particle distribution in a localized region as it orbits around, we would be able to see that by looking at raw VLBI observables and not have to make images. And what you can see here is that if you had a single hot spot orbiting, this is what Newton would see, and this is full GR ray tracing, and it goes from face on to edge on. You see that little dot there is lensed by all the gravity of the black hole. It turns into these weird crescent shapes. But more importantly, for every orbit, you see something totally different, right? So the structure is changing at asymmetric structures as a function of time. And this is work, this is really pioneering work done by Avery Broderick and Avi Loeb. Avery was a postdoc here, and Avi is, of course, a professor in the astronomy, astrophysics division. And they showed that you could potentially see these kinds of hotspots. And so with an undergraduate and also a postdoc, we started looking, and Avi and Avery and others, we started looking at a full model of a hotspot orbiting a quiescent or a stable emission structure around Sagittarius A star. And what we did was we computed the closure phase between Chile, California, and Hawaii. And you can see that over the course of an evening, you expect these spikes as this hotspot orbits around, right? It's almost like an EKG. And what you can do is you can measure this with exquisite precision on these three sites without imaging. And if we could time that orbit, we'd be able to test Einstein's theory, because, of course, the innermost stable circular orbit and its period is defined by Einstein's field equations, if you know the mass. If you know the mass. Mohammed, you asked about the mass, right? Did you ask about the mass? Yeah. So if you know the mass, then you can time it and really test whether the prediction of the ISCO is true or not. And of course, it turns out that we can do this very well. This is a kind of cartoon of what I just showed you here. And this is some work that we did back in 2009. And you can see that on the Mexico, Chile to Arizona baseline, and the Chile, Hawaii, Arizona baseline, the red here shows the expected curves based on that hotspot model. And the black points here are simulated, they're fake data that we took from that model and ran it through the array and said, what would we normally get? What measurements of the closure phase could we get from our array? And you can see that even with 4 gigabits per second, which is a kind of a primitive, we laugh to think about 4 gigabits per second now, like, oh, that was so yesterday. But at the time, it was actually pretty ambitious. But with 4 gigabit per second data capture rates, you can follow it. We're going to 64 gigabits per second. So you really get a lot of high signal to ratio here. And we're looking at these kinds of data sets now to see if we can pull this kind of trick off of looking at the period between these spikes. OK. And so finally, I'm just going to say that, can you test the Kerr metric itself? Well, it turns out that if the no-hair theorem is obeyed, the quadrupole moment of a black hole should be expressible purely in terms of the spin and the mass. And some of our theoretic colleagues, Johansson and Saltis, have tweaked this, and they've said, what if there's some epsilon parameter? What if there is some way in which we violate the no-hair theorem that's parametrizable? And they changed the metric, and it turns out that as a function of spin and as a function of this epsilon parameter, the location of the ISCO, the size of the ISCO, changes based on epsilon. So as epsilon changes, based on epsilon, as I said, the size of the ISCO changes, and also the light bending around the black hole changes as a function of epsilon. So you should be able to see the effect of violation of the no-hair theorem if you can make a very good image of the shadow. I thought I had an image of that, but I guess I don't have that here. I apologize for that. But you can see if you actually look at the GR-MHD simulations and you ask yourself, what happens if I turn epsilon to 1 or -1, it changes the shape of the shadow. And that's something that we hope to be able to image at some point. So where are we now? In April 2017, as Andy said, we made observations. We got 60 hours on the very important ALMA array. We had 8 full stations. We observed from 5 to 14 of April. We give ourselves a 10-day window. and then we only trigger 5 of those, so we get weather contingency. So if it's snowing above Alma, we just don't run, right? And of course, your threshold and your tolerance get lower and lower and lower as you get to the end, right? So at the first, you're like, oh, I don't want that weather. It's not perfect, right? And then by the time you get to the end of it, it's like, I'll take anything. It's just like, let's just get on the sky. But at first, you are quite picky. And it turns out that we just lucked out. In 2017, we got the weather gift. And we got amazing weather on almost every single day that we triggered. And that's really...
You could still only trigger 5 days.
Yeah, because we only had a certain amount of time granted. Who here does observational astronomy? Oh, you must come to the dark side. You must come. So the way this works is that if you want to get time on one of these premier sites, you have to submit into a highly competitive process. And you describe the exact observations you want to do, what you want to do with the data, the science you hope to do, and the oversubscription rate is intense. So only the top proposals get through this process. So the fact that we got 60 hours for this on ALMA was quite something at the time. So we've built a whole suite of software now. This has been done by our colleagues at Nijmegen and Radboud University. And you can see we monitor the weather above each site. We monitor the health of all the different pieces of equipment that we have at the sites. And we trigger just when everything is perfect. And we got detections to all sites. So as Andy alluded to, we have data in the can that connect every single one of our sites together. So everything worked. ALMA is very, very important. So essentially, if you have these 3 sites, and this site is extremely sensitive, then this baseline can give you detections on very short time scales. Every second, for example, you can get an interferometric detection and measure the phase. This is ALMA. This baseline, likewise, is also very sensitive. Every second, you can measure the phase on that interferometric baseline. What we do, then, we play this trick. And on this baseline, which is a weak baseline, this is maybe like a 90-meter diameter dish. This could be a 10-meter diameter dish. This might be a 12-meter diameter dish. This is going to be a very weak baseline, very difficult to integrate and detect the source in 1 second. We take out all the phase variations from these 2, which we can measure very well, which are almost entirely due to the turbulence in the atmosphere. And by doing that, we take out essentially the atmosphere above this source and above this site and above this site. So what you're seeing here is, before we do any tricks like this, you see a respectable but low-level detection here, and detection there. But after you phase stabilize this, you do this trick of subtracting the phases on the very strong ALMA baseline, you get these beautiful detections. This has made all the difference. Achilles, this is what allows small dishes to be used. All right? So we used to think you had to go to these premier sites. You had to use the best telescopes in the world. It turns out that with ALMA, you can put small dishes almost anywhere you want. And that is going to change the complexion of what we do over the next decade. Right? We're going to, instead of taking what we get, instead of looking at where the telescopes exist, we're going to engineer the next phase of the Event Horizon Telescope to give us exactly the array we want. And I'll get to that. I'll wind up with that point in just a second. The other thing here is that everybody wants to have fun with us. We're fun. So when we observe here in the red, many of our panchromatic brethren and sistren join with us. So we have sites and facilities that look at TeV, tera-electron volt photons, X-rays, infrared, and our longer wavelength compatriots join in, all to look for activity that might be correlated at these other wavelengths associated with physical processes at the black hole boundary. In 2018, we upped the ante a little bit. We went from 32 gigabits per second to 64. We added the Greenland telescope, which gives us these very wonderful north-south baselines, very useful for M87, which is a northern hemisphere source. And what allows us, again, Achilleus, to think about smaller dishes is that we have continually reinvented ourselves. We don't stick with one system. These are magnetic tapes or disks. Now we use helium-filled hard disk drives with massively parallel field programmable gate arrays. We swallow like all the possible bandwidth that's available to us from modern cryogenic receivers. And we record about 7 petabytes of data per session. This really is big data that we're working with here. Over the next 3 years, we're going to add more sites. So we're adding a site in Arizona, one in the Plateau de Bure, which I showed you. We're shifting all of our processing now to the cloud. It turns out that, why would you build a cluster? That's in the Alps. It's an array that's in the Alps that operates in our waveband. We're moving to purely cloud correlation now, so we want to ship all the data to Google, where they will post it on websites, I guess. I don't know. There are some privacy issues there, which we're grappling with. But we farm everything out to these data farms, and we can correlate all the HD data in hours instead of months. So instead of using a dedicated cluster where you have to care and feed for it, you have to provide power for it and upgrade it, we leave all that to Google now. And we make it a commodity cost, a capital expense. And we're going to higher frequencies. I already gave you that little tidbit that we've done our first 0.87 millimeter detection, or 345 gigahertz. And I'll tell you a little bit, I'm going to wind up with this dynamical imaging, because when you put telescopes anywhere you want, you can move from static images to making movies. That's what's going to happen over the next decade. We're going to leave behind this kid stuff of imaging black holes, and we're going to start making movies of them. This is what I mean. So right now, if you want to look at Sagittarius A star that is changing on timescales short compared to the rotation of the Earth, it's very difficult to do. But you can't, in the standard methods, it's difficult to do. If you use dynamical reconstruction algorithms, which we're developing here at Smithsonian and Harvard, and that's an advertisement for anyone who wants to come join our team if they want to make movies of black holes, you can do it, but you can't really track motions. But if you were able to put telescopes anywhere you want, then you can start to actually look at the rotation curve and even fill out some of these filaments as a function of time. So this is where we're going.
Faster than anything quick in real time.
Faster than anything?
This is like sped up.
Well, yeah, I think that is sped. Well, also the Earth is rotating a little faster. Touche, Andy. Yeah, everything's been sped up here, but well, these are all in synchronicity with this, right? So this is all sped up in the same amount. Right? Yeah, I'm dizzy. I'm dizzy just looking at this. Yeah.
Once the SKA comes on, can you use that as well?
That's a great. So, can you spell out what SKA means?
Square kilometer array?
I just wanted you to do that for everybody else, because maybe people don't know. So the square kilometer array is a new facility that's being built partly in Africa and partly in Australia, and it's what it says. It's going to be a square kilometer of collecting area, although not quite. The problem is that it operates at a much longer wavelength, so we can't actually tie in the square kilometer array to this work. This is strictly 1.3 millimeter and shorter. Yeah.
Is there? I would imagine there'd be an advantage to having baselines with satellites, right? Is there any work being done with? Okay.
Andy, where do you get these students? They're killing me. So, Brian, right?
Yeah.
Okay, yeah, this is exactly right. So, especially when you go to 345 gigahertz or 0.87, you want to get above as much of the atmosphere as you can, because water vapor really starts to hammer you. So if you had something in space, of course there's no atmosphere, so you can benefit from that. What you're seeing here is you're seeing the baseline coverage in purple at 345 gigahertz. So there are fewer telescopes that can go that high in frequency. So you're kind of stymied because even though you use all the telescopes you can at this frequency, you don't have maybe enough to make a good image. If you were to put a single 8-meter dish in low Earth orbit, instead of waiting 12 or 24 hours for the Earth to rotate, you have to wait 90 minutes for LEO to go all the way around. So you sweep out a whole track of baseline coverage in 90 minutes. And that allows you to fill in the Fourier plane very, very quickly. So over a night, you wind up building up a lot of Fourier spacings, not by waiting for the Earth to rotate, but by having the satellite zip around. So if you had a simulated image that looked like this is what you could do with the Earth-only baselines. This is like one kind of reconstruction. It's very difficult to get an image. But with all of this, you wind up getting a nice image of the shadow at this high frequency. So that's kind of where we're headed for space VLBI. And I hasten to add that Andrew Shale, graduate student who's leaving us for Princeton, actually a postdoc next year, Katie Bowman, and Michael Johnson, and also a new graduate student we have here, Daniel Palumbo, a first-year Harvard graduate student. They're really pushing this. In fact, Daniel Palumbo, the first-year graduate student, is leading this entire effort. And he's just submitted the first paper on space VLBI from our group. Another advertisement for us. And then, so we also want to make movies from space. So that was a static image, but we can make movies now. So this shows that hotspot orbiting around. And you can see here, as a function of time, when you have four 4-meter dishes orbiting around, this is instantaneous coverage, right? At any one moment, this is what we get. And that's enough to start making movies of this hotspot orbiting around. This is a reconstruction of the video of this movie here. So for Sagittarius A star, with enough satellites, as Brian alluded to, we can start to make movies. OK, so this is who we are. Here's a dynamical bunch. This was us 2 years ago here at Smithsonian Astrophysical Observatory down the road. We're now 200 members, 12 countries, about 30 institutes. Here's kind of a rogues gallery. This is actually one of our funders. this is someone from the Gordon and Betty Moore Foundation who visited us in Mauna Kea, and he's thankfully not really repairing the maser. This is a hydrogen maser up at the top there. This is a bunch of us. I'm not here, but this is the one place in Hawaii, one of the only places where it snows in Hawaii. This is the top of Mauna Kea. One of the only places where you can be skiing and then surfing within an hour. I believe it's only one of the few places where you can do that. This is a bunch of us. This is Laura Verticich, who designed all the hardware. Gopal Narayanan, who's at UMass. Alex Pope-Stefania, who's also at UMass. Lindy Blackburn was our postdoc, is now staff here. And this is David Sanchez, who was a graduate student in UNAM in Mexico, but is now now a staff member there. And this is Dan Maroney and his at University of Arizona, and his student Junhan Kim, who are at the South Pole Telescope, retrofitting the entire optical system to allow it to work with our array. And we're very fortunate, of course, to get a lot of support from around the world. NSF helps us a great deal here, but also the Gordon and Betty Moore Foundation and the John Templeton Foundation, and a cast of international characters that contribute here. You can find us on the EHT official website, www.eventhorizontelescope.org. That's it. Normally, I would just play a quick little movie here. Do I have time for a little movie? Well, actually, who helped me with the audio here? No, she's gone. The person who is. Well, OK, let's see if there's audio. No, it's not. It's not.
I heard it just wasn't loud enough. Probably just need to turn the volume up.
Oh, let me see if I can do that. I just like to play this because it's kind of fun. Oh. Okay, I'm going to try it. I'm going to try to back up. Okay, so I play this because this is mostly something I do at like public lectures, but I really got tired of seeing horrible depictions of black holes in movies. You know, like we're physicists, we're astronomers. Like, oh, not again. You know, like a being of pure energy, or oh, it's a portal into hell, you know. So, you know, so this is. I just like this one though. So let's see if we can see how many horrible things are in this one.
Another update. It's now been confirmed. Sources at both the Pentagon and the Department of Homeland Security are now officially describing this dark mass first seen just outside the downtown area of St. Louis as a black hole.
Black hole. It's a gravitational field so strong that even light can't escape its grip.
To straight to the point, since its emergence less than half an hour ago, the hole has consumed tearing apart surface.
You do not want to mess with a black hole, right? Okay, so just really quickly, let's just figure what the hell is going on here. Okay, so let's just figure how big does this black hole have to be? Okay, so it eats a building, and I'm figuring that the building codes are such that you have to build them so that they withstand 10 Gs, right? 10 times our gravity, okay? And it seemed like it was kind of like below the surface at 25 meters, just like going like sucking things down. Like, let's just say it's 25 meters below the surface. So in order to generate that gravitational field, the black hole mass has to be 1/10 of a billionth of the mass of the Earth, about 700 trillion kilograms. Okay, so maybe you could make a black hole about that size. But the problem is the event horizon of something that, even that large, is 1/trillionth of a meter across. It's smaller than an atom, right? So the problem here is that you've got something that's really, really massive and is smaller than an atom. So of course it would just fall to the center of the Earth with no real resistance, right? It would just like seesaw through the Earth and in one of these Lisa Jew patterns and eat. So it would come up over here, it would eat a dog, you know. And then it would you'd be like, "Where's Fido?" "I don't know," you know. You know. And then we'd go over there and eat something, and then come back. We'd all be sitting around like, "God, where all the," you know. So so I encourage everyone to spread the word that all these movies are not really very truthful. So I'm going to end here, thankfully, by sharing with you something that I think is really interesting. Jean-Pierre Luminet in 1979, I showed you the schematic diagram that he did, but he used a true computer simulation and painted with India ink on Canson negative paper, using the printouts that he got from his simulation, what this black hole would look like. This is a thin accretion disk. So the shadow you see here is mostly due to the inner edge of the accretion disk, but you can see this faint line here. That is the last photon orbit. That is the true shadow. So he had it nailed down as early as 1979, what this would look like. And then, of course, you know, Kip Thorne and company did this not too long ago. And so we're hoping in the Event Horizon Telescope to kind of contribute to this rogues gallery of black hole images. And I'm happy to take any questions. Thank you for your attention. But you guys asked a lot of questions anyway, so.
More questions for Shep?
The James Webb Telescope, will that be applicable to the EHT?
Yeah, it can't join the EHT because it's mostly infrared.
Yeah.
Right, so it's extremely capable. It's going to be amazing. We may even want to image with it as part of our multi-wavelength campaigns, but it can't join the.
Is there anything going up soon or already up that, like an 8-meter sort of satellite?
Sadly, no.
There's no plans for anything.
Well, but if there's anybody in the audience who's going to be reviewing NASA proposals, we are putting in a proposal in the next month or so to do some technical development that would lead to the first mission. So one of the things that you have to watch out for is how do you put a really stable clock in space? Because those masers I was showing you weigh 200 kilograms or 500 kilograms, depending on the model. That's a lot of weight to take into space. And if we can phase stabilize a crystal in space using a laser link, then we'd be able to put something much lighter into space and get the stability of whatever was conditioning it via laser from the surface of the Earth. And that's what we're looking at now. We're trying to find bright young people, hint, who would like to do that.
If you start adding in space telescopes and you could increase the resolution, so would there be potentially a third black hole that you'd be interested in looking at?
What a great question. Yeah, I don't have the slide here, but well, so first of all, LEO orbit doesn't help you at all because LEO is just skimming the surface of the Earth. But if you go to MEO, like mid-Earth orbit, or geostationary orbit, then you actually get a much better resolution, right? So GEO is like 22,000 kilometers, I think, or something like that. So it's a couple of Earth radii away. Then you can really get better resolution. There is a telescope called Radioastron, which operates at longer wavelengths, like 1.3 centimeters, and that goes out to 7 Earth radii in an elliptical orbit. They actually have the record, but we don't talk about that. No, they have the record, but in a different wave band. So, and it's important to note that because of the self-absorbed plasma that exists around the black hole, even though they have better raw lambda over d, better angular resolution, they can't see all the way to the photon orbit. They see this kind of opaque last scattering surface because the synchrotron emission is opaque to itself. So a photon at those low frequencies hits one of the relativistic electrons and scatters before the mean free path allows it to escape to infinity.
More questions?
Well, thank you very much.
Let's thank Shep for an
Oh,
amazing talk.
thank you. I will, but you know what?
Can't wait to hear the data. See the data.
Soon. Soon. Yeah. I mean, we're locking things down pretty tightly, but it's we're on our way.
Yeah, if you ever need a physics person to sign students, students can't have to have somebody to advise, right? They have to have an advisor. Can they work?
Actually, so